Good morning and welcome live to Lincoln, Nebraska for the final presentation of the William McEllhiney Distinguished Lecture Series. Today we'll be broadcasting over the web. We have a toll-free number. It's 1-800-332-0265. Operators are standing by to take your calls. You will give them the password for groundwater and give your questions about this presentation. What I would ask you to do is hold your questions till the end of the presentation, because it is quite lengthy and there's a lot of detailed information in here. So with that being said, I'll give you the number one more time. It's up on our screen, 1-800-332-0265. The password is groundwater. Well, welcome to the 2011 William McEllhiney Lecture Series. Before we start, I want to tell you just a little bit about William McEllhiney. Mr. McEllhiney was one of the founding presidents of the National Groundwater Association. He was also a civil engineer and a groundwater contractor. And in 1948, Mr. McEllhiney and some of the other founders of the association, they saw a real benefit of having a national organization where you would have information that was disseminated throughout the country and people could share ideas and new developments. As of 2005, Franklin Electric has saw the value of this program, and they've picked up the cost of this. Now, since January 1st of this year, I've been in 28 different states and 3 foreign countries, and Franklin Electric has picked up the travel and reimbursed the NGWREF for all this. The way the McEllhiney Lecture Series works is annually a program where a presenter is chosen and asked to present their findings to the country. And I was really honored to be selected this year as the 11th McEllhiney Lecturer, and I've joined a distinguished group of people who are considered leaders of the industry, and I'm very honored to be included in this group. I want to tell you a little bit about myself here. My name is Tom Christofferson. I am the program manager for water well standards in the state of Nebraska, and since 1999 I've been involved with and an integral part of the Nebraska Grout Force Test Study. I was a water well contractor for over 20 years before I went to work for the state of Nebraska as a field superintendent and an inspector, and now I'm the program manager, so I have a wealth of knowledge about how wells are constructed and how wells are regulated. Our series today is called the Nebraska Grout Task Force Research. Appropriately, it's titled Unexpected Results and New Solutions. And this lecture series is about a research project that was different than any research project you've ever known. Most research projects start off with a hypothesis, a budget, and a well-formulated idea where they want to end up. Well, this research didn't start out that way. This research was developed upon need, and need about new solutions for unexpected results. It's more of a story, so if you stay with me for the next hour and 15 minutes, I'm going to tell you a really neat story about what happened to me in my state. I want to visit with a little bit for our folks who are joining us over the web about Nebraska. You see where Nebraska is located, right in the heartland of the U.S. Some facts about Nebraska. Us locals pronounce it Nebraska, not Nebraska, not Nebraska, but Nebraska. It comes from an Oto-Indian term meaning flat water. Our size of our country, I've been across the country and the world, so excuse me for that. The size of our state's pretty modest. We're 490 miles by 240 miles, about 200,000 square kilometers. And our highest point of elevation is about 5,400 feet above sea level. Our lowest point is 3,200 feet above sea level. So if you take that 2,000 feet of elevation, stretch it over 490 miles, you can see why the Oto Indians called it flat water. There's not much drop there. Nebraska is known as a groundwater generator. For every gallon that flows into our state, 4 leave our state. That's because we're ideally located right in the middle of what the pioneers called the Great Inland Sea. Most of our deposits are sedimentary, and that allows us to create water, to store water. We are perfectly situated. between the Rocky Mountains to the west and the Gulf of Mexico to the south. When the storms come over the mountains, the cold fronts are very dry, and they clash with this warm, moist air mass from the Gulf, and we get tremendous thunderstorms in our state, blizzards in the wintertime. So we get that precipitation in big amounts. Some more facts about Nebraska. We got about 1.7 million people in our state. 1.2 million of those people rely on groundwater for their daily use. 2/3 of our population is located in the eastern portion, or the eastern quarter of Nebraska, mostly in two counties of Lancaster and Douglas County. Our economy is agriculture based. We have industry and manufacturing that supports that agriculture. We average a $3.2 billion in income in our state. 40% of that comes from the sale of cattle and calves. 31% of that comes from the growing of corn to feed those cattle and calves and producing ethanol and other corn products in our state. 14% of it comes from growing and selling of soybeans. And 4.3% comes from the sale of hogs. Our natural resources, our greatest natural resource, is our groundwater. We don't have the forests, we don't have the mountains, we don't have the beautiful sceneries that I've seen across the country and other states, but we do have more groundwater than a lot of states combined. The USGS estimates that if we could bring our groundwater to the surface, we would have a lake surface larger than Lake Superior, Lake Michigan, and Lake Huron combined. It would be the biggest lake between the Great Lakes and the Great Salt Lake. For our grains, we have 94,000 registered irrigation wells in our state. Disperse those over 93 counties, we average about 1,000 irrigation wells per county. As of 2006, 40% of our cropland was irrigated, and we have just either surpassed or matched California as the leading groundwater irrigating state in the country. Livestock, we have the unique designation of having more cows in Nebraska than people. I've always said, if cows could vote, we'd only be eating chicken in Nebraska. To give you an idea about our groundwater use, you can see that 92% of our groundwater usage is for irrigation. When our center pivots are pumping, we're using about 7.5 billion gallons of water per day. That's a huge amount of water. Our domestic usage, about 5% of that total, about 400 million gallons of water for our cities and towns and private farms. Our livestock get about 110 million gallons per day, and industry gets about 11 million gallons a day. So you see we're very dependent on groundwater to support our income. Our concerns for our groundwater pollution are chemicals and other bacteria that could cause our water to be undrinkable. So let me tell you, before 1986 in this state, to drill a water well, all you needed was a driver's license and a drill rig. There was no statewide standards, there was no licensing. So our legislature decided, in order to protect this great natural resource of ours, they passed the Water Well Standards and Contractors Licensing Act. The purpose of that act was to protect the groundwater, and another purpose was to promote the efficient usage of that groundwater. In 1999, after we've had standards for almost 11 years, we determined our first grout standard were pretty inadequate. Our first grout standard was a half a pound of bentonite per gallon of water. It was not sufficient in order to protect our groundwater. So we needed to improve our grouting and improve our requirements. We looked at other states for case histories and field experience and what they did for protecting their groundwater. And what we found was, they told us, rely on this. Full-length grout provides maximum protection of the groundwater. When in doubt, just grout your hole. And all grout materials are pretty much alike. And what this did, folks, this put us in a conventional thinking mode. We kind of locked our brains in a box. And we took what other people told us for fact. We looked at the prevailing technologies for how grouts were studied prior to 1999, we found out that most of them studied in laboratories. These were in controlled environments. There were some in situ studies that were done, but they were historically destructive, they were limited in their depth of view, and they were segmented. What they used to verify their findings in these laboratory studies, they used a technique called bond logging, and that's when they put an acoustic ping in the casing to see if there is any hollow portion behind that casing. If the grout was present, that ping would come back quickly. If the grout was absent, it took a longer time for that echo to come back. So that's how they verified their beliefs that all grout materials are alike. Full-length grout provides maximum protection of the groundwater. We were told that the two products we should look at were cement grouts and bentonite grouts. Cement grouts because they provide super structural stability to the well casing of the borehole, and bentonite grouts because they're more flexible, they're more pliable, and in the sedimentary deposits, they will rehydrate. So we looked at these. Cement grouts we found were considered a universal grout. You could use them in all kinds of applications. Water quality didn't affect them. Ground quality didn't affect them. Their drawback was they had limited cracking, but it was mostly a horizontal cracking, and it bonds to all types of materials. I mean, anybody who's poured a sidewalk or mixed concrete knows that concrete sticks to their shovels, sticks to their wheelbarrows. It's really nasty stuff. The bentonite grouts, we were told, they would also crack, but they were limited in that cracking and shrinkage. But the big drawback was you could only pump about 20–25% of active solids in a bentonite grout. But the redeeming factor was bentonites rehydrate when they get wet. That's what they do. They swell up and they'll repair themselves. So, based on this conventional thinking, the state revised the standard in 1999, and we adopted the national belief. We took as the bentonite grouts a 20% active solids bentonite. It had a permeability standard of 1 × 10⁻⁷ centimeters per second. And we felt pretty good about this. We now joined the rest of the country in providing groundwater protection. Well, shortly after that, the bentonite industries came to us and said, we've put a lot of money and a lot of research in a grout product that's less than 20% solids. It has the same characteristics as a 20% solids, has the same gel strength, has the same permeability standard, and now they can't use it in Nebraska. So, with the bentonite industry's cooperation, the state of Nebraska decided to construct the ultimate well. This was going to be the way everybody should make wells. And for the first time, we held a demonstration at the University of Nebraska. What you're seeing on the screen is the first time anywhere a water well has been filmed from the inside out during its construction. By using clear PVC casing that was normally used for food handling, processed cheese and milks and things, we took advantage of this clear PVC to see how grouts would be affected in the ground and how to properly make the perfect well. What you're seeing on the video now is the gravel pack has just been placed over the top of the screen, and we've just opened a bag of bentonite chips and poured those down the borehole. They're a free fall chip. We poured them in a real deliberate fashion, and what we really wanted to see was how these chips form a seal, because this is a product we use a lot in Nebraska and have used a lot since 1986. We wanted to see if the chips would align themselves, if they would make a good seal, if they would bridge, if they would impact the gravel pack, and as you can see, the chips kind of find their own place in the borehole. They align themselves in a real nice, orderly fashion, and they make a good, tight, homogeneous, uniform seal. We were really happy about this. This was really encouraging. So now we decided to start pumping our grout slurry. And you can see our grout slurry is coming up in a very quick manner, just like you want bentonite grouts to do. They come up the borehole in a rapid fashion. They evacuate everything out in front of them that's liquid. And you can see the grout itself has got a nice kind of a pudding consistency to the grout. It's looking really good. In fact, it came up the borehole so fast, it outpaced our camera. So once we caught up with the top of the column, we watched how the grout migrated up the borehole. When the grout would meet an obstruction, say a piece of bentonite that stuck to the side of the borehole wall, or some cuttings that didn't quite get cleaned out, the grout, instead of evacuating it, would just entomb it. It would surround it and place it and kind of make it part of the grout column. This was the ultimate well, folks. This was how we make monitoring wells in Nebraska. This is full-length grout to provide maximum protection to the groundwater. We were very excited about this. Wow, look what we did. Until we went back 14 months later to follow up on this. Most of that grout column was missing. It's gone. And this is how you get started in research. You create a demonstration illustrating this industry's best standards, their best science, with a technology that's never been used before, the clear casing. Now we can see what's happening. And we found out that grouts don't stay static. So, to verify our standards and to move forward, we started thinking about other conventional thinking and a historical perspective on this. All these statements you see on the screen were true at one time in the Earth's history. The sun revolves around the Earth. That was a tough one to get people not to believe. The world is flat, Columbus. You go over there, you're going to fall off. And if man was meant to fly, God would have given him wings. And I tell you what, if that would have not been true, I'd have had a lot of train miles and shoe leather worn out this year. Because I'm really glad folks would challenge the conventional thinking. So this is what we did in Nebraska. Our study is going to change that. Our study is going to utilize this clear casing where we can see things that's never been seen before. It's a visual component. We're going to look the full length of the borehole. We're going to take this out in the real world. We're going to do in situ testing for the first time. And nothing's going to be destroyed because all we're doing is taking pictures. We're just doing observations. We can dye test this. We thought we could keep these wells for a unlimited amount of time. And in reality, we got about 8 years. And after 8 years, the casing gets cloudy and you can't get a picture. If you can't get a picture, your visual study's over. But we can use it for all types of grout materials, and we can put it in all kinds of geologic sites, and it's effective for all kinds of grout materials. And in fact, some of the findings out of this led to new discoveries beyond this study. And we'll talk a little bit more about that later on. Early on, it was felt that our study needed a mission statement. And the mission statement to keep us focused was, we are going to look at the products used for grouting wells, not the people who make the products. We're not comparing manufacturers, we're comparing bentonites, certain grades of bentonites, certain degrees of cements, and we want to study the properties and how these react. And because of that, we got great cooperation from the industry. The bentonite industries and cement industries gave us all the information and the support we needed. One thing we learned, when we made our ultimate well at UNL, we didn't do any background testing because it wasn't research. It was a demonstration of the ultimate well. So when things went bad, we found out that we didn't do anything for testing the groundwater. Were there contaminants? Were there conditions that would affect grouts? We didn't know. So when we chose our study sites in our state, our university went out and they took core samples of the soils. We studied those for particle size, moisture content, for any contaminants that would degrade a grout. We also studied the water quality for those contaminants and those parameters. And then when we were done with that boring, we put a monitoring well in that site, and we would monitor the fluctuations of the static water table. What increases in water table or decreases in water table affect our grouts? This is what we're going to find out. Here's our study sites. The eastern part of Nebraska, with the yellow circle and the green triangle, is going to study grouts in the glacial deposits of Nebraska. These soils have been influenced by glacial melt. They have a lot of fat clays, a lot of tight clays. They have perched water tables. They get a lot of moisture, so they are a high moisture content area of our state. It's where most of our population is centered, so we're going to study wells in that portion of it. The Grand Island site with the red square is going to study wells in the Platte Valley alluvium, the sands and gravels of our state, where most of that irrigation water is pumped from. So we're going to see how fluctuations in that water table and those deposits are affecting grouts. And then the little blue triangle and the purple circle are going to study grouts in the Panhandle or the Ogallala formations. The soils and that part of the state gets less water than the east part. We get 8 to 12 inches of moisture on average in Scotts Bluff, compared to 38 to 40 inches in Lincoln and Omaha. So we got very diverse geology, we got diverse climates, we're ready to go. And here's our sites. The northeast site, the major characteristic of the Pilger site is that it does have perched water table potentials, and it has 3 lust deposits which are very absorbent materials in the unsaturated zone. The central study area, its major feature was high fluctuations in the groundwater table, like I talked about. When those irrigation wells are pumping 7.5 billion gallons a day, that water table drops in the summertime, anywhere from 15 to 25 feet. When those irrigation wells shut off in the fall, by the springtime, that water table comes back. So we have a very dry zone that's recovering. The southwest area we studied because it was very parched soils. Those soils were dry, they were absorbent, they were fine-grained, and we had a very unique situation where we could have a single aquifer system that was close to the surface to study these. These wells that we studied in this part of the research were all less than 100 foot deep. They were held to that because of the cost of the casing. The casing was about $10 to $11 per foot. So we had the expenses we had to stay in tact with. And then the fourth feature of the southwest area is where we got into looking at grouts for our geosystems. And this is at Lake McEllhiney, the visitor center. And this unique situation gave us a very deep water table. We had an extended vadosome, so we could see how does our grout stand up to this dry environment without much water. To give you an example, this is how monitoring wells are constructed in Nebraska. This is an illustration of exactly what you saw in our video. Our screen's covered with gravel just above the top of it. There's that bentonite chip seal we saw in the video as it dropped down on the gravel pack, and then our grout column went from there to the surface. Full-length grout providing maximum groundwater protection. One thing we learned in the university study is when we wanted to find out how badly the grout was cracked, we tried to pour dye down the hole, but the dye went everywhere. So our task force came up with a containment vessel that we designed about a 4-foot deep flush buried cover, and in the bottom of that cover we poured about a foot of gravel, and our dye tube terminated in that gravel. So when we dye tested this, the dye would load the gravel and it would put a pressure, an equalized pressure on top of the grout column, so we would get a uniform standard looking at validating our grouts. The goal of this visual study was to be very objective analysis, so we went foot by foot of the borehole. Our camera surveys were performed 24 hours after the grout was placed, so we got a new picture. We came back 30 days later, 60 days later, 90 days later, so we got a nice time-lapse photography on how all this grout ages. And in doing that, we had to come up with a numerical code to put this on a graph. So we could chart it. I want to show you what that visual assessment graph looks like. You can see on the left-hand side, if the grout is given a value of 0, that means there's no data. Either you're in the flush mount or there was no data recorded. If you have a 1, that means your grout was very good. It looked just like it was pumped the day it was made. If it was given a 2, we saw some cracks. We saw some developments happening in the grout, but we still felt pretty good about its ability to perform. If you saw a 3, that meant the grout was no longer considered a grout. It had channels, it had voids, it had detachments. So what you're seeing here on this screen over here, this is an example of our northeast site, and you can see up here we had really no data. When we got over to here, from 5 to 10 feet, our grout was already degraded. Okay, it was a bad grout until we got to a little bit of a perch table right here at 11 feet, and then right away, once we got through this confining layer right here, our grout went bad again. Until we got down to another perch table, and we saw our grout come back to a 2. Pretty acceptable. We got through this confining layer, and bang, our grout goes bad again, until we get down here to static water level. Well, what that tells us is, this is the first clue about what's happening to grouts. This is the first thing that we should have been warned of about when things go bad. To give you an example, Code 1 is a good grout. That's a 24-hour picture of a bentonite slurry. And that looks just like a downhole video camera of a PVC well. There's no wrinkles, there's no inconsistencies, there's no cracks. It's almost letter perfect. That's a 24-hour picture. Code 2 on a bentonite is about a 60-day picture where we're starting to see cracks perform, starting to see some separations, we're starting to see a little bit of division, but the cracks aren't connected. We still feel it's got a good potential for being a sealable grout. But Code 3 is a picture after 90 days. And we see huge chunks of bentonite missing. We see the cracks are connected. And we no longer feel that this would provide us any groundwater protection. We looked at bentonite chips. We had some wells that were full-length grouted with chips, just to see what that would look like. Once again, a Code 1, the bentonite chips are nice and tight. They look solid. You see the discoloration of the chips as they melted together. 24-hour picture once again. Code 2 was a 60-day picture where you see the chips are kind of pulling apart, separating, but they're still in place. But Code 3, we're showing you a picture of a major void in a chip seal. And this is where the borehole was either, we had a blockage, or we had a bridging, or we had a big void behind our grout column. And either way, it's either a product or a placement issue. This is to show you how big a void you can have in a 70% active reactive solids grout. And that was over a 90-day picture. Cements are entirely a different story. Okay? Code 1 was a 24-hour picture. It's a neat cement that's nice and tight. There's no cracks, there's no wrinkles, there's no discoloration. Code 2 is a picture less than 2 weeks old. And we're already seeing vertical cracking. Now, we were told horizontal cracking is what you can expect in cements. It's a stress crack. We weren't expecting to see vertical cracking, straight up and down. That's 2 weeks. And the Code 3 was a 30-day picture. So cement grouts get to their static condition within 30 days. Bentonites take about 90 days. Once the cement's cracked, it's cracked. We're seeing detachments where the casing is pulled away, and we're seeing big voids. And what you're seeing down in the lower right-hand corner, that's a placement problem. That's where the trimming was plugged and was reinserted, and there was a water bubble right in the middle of your grout column. Okay? So it's not only just a product we're looking at, it's placement. Now, our next challenge, when we went to study the geo-exchange system for closed loops, nobody makes closed loop piping that's clear, and it's never big enough to put a camera in. So in order to study the grout, we had to insert a clear sight glass right in the middle of our loops. And this did two things. This allowed us to look at the grout full length, but it also allowed us to look at a grout in a larger than normal situation of a borehole. We had to drill almost a 10.5 inch borehole for 2 3/4 inch loops, and nobody does that in the real world. So we're looking at an overgrouting situation and how that would affect our grouts. And because these loops had to be used, we had to modify our dye tank. Our dye tube actually had to go down into the borehole where our dye would be loaded right on top of the grout column. Now here's an illustration. This is out of our geo loop system in Lake McEllhiney. The picture on the left, you see the top of the grout column 103 feet below the surface. That's full-length grout, folks. That's supposed to provide maximum protection of the groundwater. This is in the site that had a very extended albedo zone. Before 1999, in Nebraska, we would gravel pack loops, and then we would top it off with 30 feet of this chip bentonite. But in order to provide maximum protection, we went to full-length grout. When we did, our contractors told us that our loops are no longer working. And it's because that grout is insulating the loops. Well, getting caught in the conventional thinking, everybody was pretty sure that's what was happening until we come up with this picture. It's not the grout that insulated the loops, it's the lack of grout that insulated the loops. These loops were hanging in dead air, and for a loop to transfer heat, it has to have contact with the ground. So when our grouts dried out and degraded, not only did it compromise the groundwater protection, it compromised the performance of our geosystems. Now, further to illustrate that, on the right hand picture, we went another foot down the borehole and we found a family of bugs living in it. Okay? My good friend Ron Peterson from the bentonite industry looked at this and he said, this is conclusive evidence that bentonite is not harmful to wildlife. So he's trying to make a good point. He's trying to put a good spin on a bad situation, but really, if there's bugs living in your borehole 104 feet below ground, you have no chance of providing groundwater protection with that kind of grout material. So after all our studies were done, we tabulated our visual assessments, and these are the recipes that the state of Nebraska approved for grouting wells at the time. Bentonite chips looked like it did the best job. It came in just at a little over a 1. Okay, so it provided us a good representative seal. A recipe of neat cement with 6 gallons was something we had proposed in our standards, so we studied that, and it came in at about a 1.2. Cement with bentonite was a little further down the road, 1.4, and you can see this is kind of a nice 45-degree slope, but if you look at the bottom of the chart, the third one up is Bentonite Slurry, less than 20% solids. That's the slurry that started the whole thing. That was just as good as all the rest of them. And you can see it's averaging over a 2 to 2.2. Now there's recipes in there that are averaging over 2.6, almost a 2.8. If you're averaging over a 1-year study a 2.8 on the condition of your grout, it's no longer a grout. It's not even a good annular fill. So we are seeing some things here. We're eliminating some things. We're coming to some preliminary conclusions, but we need to validate it. Because ours is a visual study and bond logging is not going to work to validate our process, we chose the dye testing. The dye will show you where your cracks in your grout lead. We asked the state of Ohio, who's been doing dye testing for 20 years or so, what to use, and they said use a green colored dye. Green is not a natural color for groundwater. If you've got green in the groundwater, it's pretty bad. So there are other dyes that are oranges and browns and reds, and they could be confused with iron deposits. So we chose a fluorescent green dye. Our procedure was to dye test these wells for an hour or until our dye tank ran dry. We had 200 gallons of dye mixed up, whichever came first. We would meter the volume that was used and the time it took for that dye tank to run out. And what that did, it allowed us to calculate proposed maximum depth the dye could be detected. How far would it really travel in a certain period of time, and how much percentage of the grout column would be penetrated by that dye. And now you're going to see the first horror picture from the study. What you're seeing is a dye test, and that's green dye flowing right out of our dye tube. We're dye testing a bentonite slurry, and we're just coming out of the flush mount. Now this green dye is flowing about 5 to 6 gallons a minute. It's going down the borehole faster than we can show our camera. You can see the grout is cracked. It's detached. Dye is not only flowing through the grout, it's flowing between the grout and the casing. This is how we construct monitoring wells for cleaning up groundwater at the time. This was maximum grouting, providing maximum protection, full-length grout. Well, we watched this to about 9 feet, and we got pretty shocked, but now we're starting to see some ponding coming up in the borehole. And we're feeling, hey, maybe our grout column is intact at the bottom. We kept watching, but what happened was that wasn't ponding. The dye ran so fast it took the gravel out of the flush mount and took it down the borehole and bridged. That's how big the cracks were in this 20% grout. So we kept watching, hoping, and it kept looking pretty dim until we get down here pretty close to the static water table, and we do actually see ponding take effect. We do see some good news, folks. Why do I say that? Because if we don't see ponding, we know that the grout column is shot clear to the aquifer. This dye would have gone out in the aquifer. We would have never got any trace of it back. But when you see ponding taking effect, you know something's happening in the bottom that's holding that column from getting to our production zone. And if you watch the screen on the left-hand side, you'll start to see the borehole fill. So this gives us another clue. Not the entire length of the borehole is damaged. Here's another unexpected result. The screen on the left is a snapshot from that video. We get to 68 feet, we see this nice illustrated crack. Boy, look at that green dye. That's pretty easy to see right there. So we took a picture. We came back a week later. There's that green dye in that crack. Came back a month later. Same green dye, same crack. We came back 3 months later. Same green dye, same crack. And this is where we learned that bentonite slurries will not rehydrate. Once they're cracked, they're cracked. They're not coming back. Now that's different from what we were told. We were told bentonites have this absorbent quality. They get wet, they want to rehydrate and reswell. It's undetermined why this happens. It may be because in order to mix a grout slurry, you have to have shearing action to drive the water into the particle. Then maybe there's retardants built into the grout that keeps it from flashing in the grouter. But for whatever reason, if a bentonite slurry cracks, it cracks and is not coming back. A new unexpected result. I wanted to show you this slide. This is more of a site comparison. If we can go over here to the screen. This is from the northeast, the central, and the southwest. And this is based on cement grouts. And you're going to see on every chart, on every average, the northeast is at the top. The dye penetrated not as far in the northeast as it did in the southwest. In every instance, the southwest, the dye went further. This is a cement bentonite recipe. This is concrete, neat cement 1, neat cement 2, and sand cement. But when we stepped back and looked at this, we noticed there's something missing here. In the central, we don't have any movement in a sand cement. This is where we discovered we matched a grout material, sand cement, with the material outside in the borehole. Remember I told you the central was all sands and gravels? So these two matched, and we got a really good result on how this grout was going to progress. Kind of looks like a football play, doesn't it? X's and O's and all this stuff. Okay, now this chart, just to re-illustrate that, based on cements again, on 1 hour and 24-hour movement, I want to show you this. This bar here is how far the die moved in 1 hour. Okay? This bar here is how far it moved in 24 hours. In almost every instance, this die went a lot farther in 24 hours than it did in 1 hour. In these two, in the glacial, the southwest, this die has gone behind our column. It's already dissipated out. But look at here. This is alluvial, glacial, and southwest sites. In the alluvial site, the sand cement, we had no movement in an hour, and we had no movement in 24 hours. We finally matched the grout material with the borehole material. Another unexpected result. I showed you this chart just to give you an illustration not to trust your eyes. The column on the left, the performance column, is based on the results of the die testing. The next column, the visual column, is based on what we thought we saw. And you'll see that we didn't pick a winner. Every grout we give a value to performed differently. And that's to tell you that not all cracks are connected. Not all visual things are as bad as they look. Some look better. For example, the sand cement performed a lot better than what we thought it looked like. We saw some cracks and separations when we die tested it. It did better overall than anything. And the chips, which we thought looked better than anything, did slightly worse. But if you look at the chart again, at the bottom, to the very bottom, Bentonite slurry, less than 20%. Closed loop bentonite, equal to 20%. These are high water slurries. We're seeing some indications here that solids are playing a role in how grouts perform. Our third unexpected result is we found out that neat cements will blow right through a bentonite chip seal. And this is another way we make monitoring wells. If you put a chip seal down like we saw in the video, right above your gravel pack, and then your grout column is neat cement, this neat cement has enough weight and enough characteristics, it divides the bentonite chips and it gets right down into the production zone. To illustrate that, here's another video. Now in the middle of your screen, you see the white chips as they were placed. These chips were given about 45 minutes to an hour to hydrate before we put any grout column on top of them. Now 45 minutes to an hour is probably not enough time to fully hydrate a chip, but there are conditions in Nebraska where you can't leave the borehole open much longer than that or it becomes unstable. So we went ahead and we put our grout column in there, and you see the black lines in between those white chips, that's neat cement. And you see how the neat cement has just divided the chips and forced its way and intruded right through a partially hydrated bentonite chip seal. Not only did it do that, it kept migrating right down into the gravel pack. You see the gray matter in between the grains of sand? That's our neat cement. And if you keep watching it, you see the cement cracks. So now we have a product that's designed to protect the ground, water, full-length grout, that has penetrated our primary seal, gone down into the production zone, and cracked. We have a pathway. What we're recommending is we have to protect those chips with a real fine blotter sand, so that keeps that neat cement away from the from the bentonite, we won't have that chemical reaction between sodium and calcium. Slow that column down and let it solidify before it gets into our production zone. So grout compositions. Remember that grout that was just as good as the rest of them? Well, it was. That less than 20% was just as good as a 20% or a 30%. Problem is, none of them performed worth a darn. The 16% grout cracked quicker. Took the 30% grout a little longer to crack, but they still ended up in the same position. Pure bentonite solids as a slurry will not rehydrate when they're damaged. They are inadequate in the vadose zone because of the wicking effect. The vadose zone has a dynamic of it's always pulling for water. And if it pulls water out of it, let's say a 20% water slurry, and you have 80% water slurry, 20% bentonite, you pull the water out, you've got 80% open area. And that dynamic goes on 24 hours a day, 7 days a week, forever. So a bentonite slurry in that unsaturated zone is not going to provide the protection we're looking for. Now the bentonite chips, here's another unexpected result. The bentonite chips do crack, but we discovered they do rehydrate. They're a raw bentonite product. They're over 65 to 70% reactive solids in the bentonite chip. And that Grand Island site where we had high fluctuations of groundwater, we saw in the end of the irrigation season that the grout of the bentonite chips would pull apart. And by the springtime, when the water table came back up, they'd come back together. And we saw that very consistently for 8 years. It never left that dynamic. So we feel really great about the possibility of a bentonite chip rehydrating and providing that maximum protection. But they're time consuming to put in the borehole, takes a long time to place, and they can be very difficult if the borehole's not big enough. The cement-based grouts. We really like cement-based grouts for structural stability. A cement may crack on you, but it won't leave. If a bentonite cracks and you have that 80% void space, it's gone. A cement stays solid in the borehole, it's where you left it. So we like it for structural stability on the top of the borehole. It solidifies the casing, it prevents the casing from cracking if it's impacted at the surface, but we also discovered that cements do not bond to PVC, which is something else the industry didn't expect. Well, and we'll talk about that in a later slide. So what do these results really tell us? All right? What they tell us is portions of the borehole are adequately protected, portions of the borehole are not adequately protected. Things are different than what the industry really thought. So in 2005, the task force asked the University of Nebraska to study this, just the unsaturated zone. And a man named Will Myers for the University of Nebraska determined that the biggest components that affect grouts are the particle size of the unsaturated zone and what makes up that particle. If it's a grain of sand or if it's a grain of silt, is a total different dynamic. The sand doesn't absorb anything, but the silt will. And the moisture content of that vadose zone, annual precipitation plays a real big role in that. If the saturated zone is constantly dried out like we have out west, and it's a silt and it's a clay, super absorbent material, and it's disastrous to a high water slurry. If it's a clay that's in the northeast, that's a real tight clay that gets a lot of moisture, you have a little bit better result for a high water slurry. So now we've narrowed our focus. If we want to provide maximum protection to the groundwater, we've got to focus from the groundwater table up and find out just what's going on for that dynamic. So that leads us into the vadose zone study of 2008 and 2009. Now what's different? What is different about the vadose zone study? Well, a couple things. Like I said, we're just looking at the water table to the surface. And now we're looking at different methods of construction. The grout study was based on mud rotary, because we're a mud rotary state. That's how our wells are drilled. But because we're having such a challenge with our environmental wells, we decided to look at hollow stem augers. and direct push. And this is technology used for constructing, monitoring, and cleanup wells. So we have different methods, and now we're looking for different recipes. Began planning this in 2007, and we came up with 4 parameters we have to match for the Vadozone study. We'd have to find materials that would resist cracking, be easily placed, be economical, and readily available. Okay, if you can't match all 4 of these, it's not going to work for us. And early on, we determined we could find materials that would resist cracking. That's not the problem. The problem is we couldn't afford them, we couldn't get them, and nobody had the equipment to place them. So we had to find materials in our state for our contractors that would match all 4 of these parameters. And here was, the state had 3 designs they wanted to look at. Our environmental folks had 4 designs. They were really concerned about their industry. Our partners in this from the bentonite industry was Wild Bend, Setco, and Baroid. Each had 3 recipes to look at. The direct push folks had 2 for a total of 18 wells per site. And then, as a concern for our geothermal contractors, GeoExchange, we went back to 2 sites in the southwest and in the northeast area of the state. And we went back and looked at gravel packing these loops and putting chips around the top for 2 reasons. We already had wells that were constructed like this, and we had to study this to see if we had potential problems in the future. And 2, we had to see why these sand-packed wells performed a lot better than the geothermal grout wells that were grouted to the surface. So the mixes the state wanted to look at. Mix number 1 is a recipe we got from the state of Kansas. And this came right out of their oil patch, and it was basically a cement bentonite with a lot of high solids in it. 100 pounds of sand for a bag of cement and 5 pounds of bentonite. The next thing our contractors wanted us to look at was drill cuttings. They said, hey, put back the material and borehole you took out. If you're trying to match things, it's got to be a natural match. So we did. We studied drill cuttings. Then the third thing we were really concerned about was our standard for constructing domestic wells in Nebraska. And this is where we would gravel pack to within 10 feet of the surface and top it off with a chip seal. We had to see if those grouts were performing adequately to protect our citizens. The environmental folks, they had the answers. They said, Tom, mix number 1, mix number 2, that's going to do it. That's going to be it. We studied it. We had great success over the years. We really like this. But in order to find something else, just in case, they came up with a really high solids slurry of 450 pounds of sand for 1 50-pound bag of bentonite. That's a 9-to-1 ratio. Okay, that's really high solids. And then they came up with a dry mixture. They're going to mix 3 parts of sand with 1 part of bentonite, and they're trying to match the grain sizes. The granular bentonite's about the same size as masonry sand. Wild Bend looked at a really, really high bentonite content for its cement. They put a bag of bentonite with a bag of cement to see if that would reduce the heat of hydration and the cracking. They also went with a 400-pound high solid slurry bentonite, and their dry mix, they went with a 1 part chip, 1 part pea gravel. Once again, trying to match the sizes. And the pea gravel is an inert solids. There's no reactivity to it. It's going to stay at the same condition it was originally created. The 1 part chip we like because it was that dynamic, it would rehydrate. So we're going to see if we can create a high solids dry slurry. Setco went with a real high water content bentonite. They only put a 1-to-1 ratio of sand to bentonite, and they added a lot of polymer, seeing if the polymer would help the bentonite grouts. Then they really cut the water down, and they put in 1 bag of bentonite, 10 gallons of water. Their dry mix, they went by volume. Okay, 5-gallon bucket full of sand, 5-gallon bucket full of bentonite, and it was a 1-to-1 ratio. Baroid is a division of Halliburton. Halliburton's a major cement grouting manufacturer, so they focused on cements. trying to solve our cement issues. And what they did, they really cut down the water content. Bare minimum water, 5.2 gallons for a bag of cement. And then they put in some of their IDP product that would retard shrinkage and reduce cracking. And then they added one that just has a ponzolotic additive, kind of a fly ash component. Their dry mix was a 1-to-1 ratio, only it was by weight. 50 pounds of sand to 50 pounds of granular bentonite. Direct push, folks, they didn't have much choice. They used a 20% bentonite slurry, and they pre-treated their grout with soda ash, and then they left one untreated. And this little tube you see in the picture, that's their grout tube. Now you don't get a lot of solids through a tube like that. It's a pretty small annular space. The grout heat exchanger, we went back to what we did in 1999. You're seeing the picture on the lower right, where we're just free-falling sand through a kind of a bentonite drill fluid. We're trying to recreate a dirty sand, is what we're doing here. And this took a really long time to gravel pack this loop. But it's replicating what the standard was in Nebraska before full-length grout. So here are the results. All right. This looks pretty good. These are 18 recipes. When we dye tested it at Grand Island, we only had 3 of them hit groundwater in an hour. That's pretty good. We had 3 more that are on their way, and by knowing how grout moves, we calculated, we eliminated 6. 6 out of 18 were no longer considered a viable recipe. Well, that's 667. That's pretty good average. And we felt good about that until we went to Pilger. Okay. Now, the northeast site, none of them touched groundwater in an hour. However, we had 7 of them over 50% of the borehole. We had another 3 or 4 that were over 20% down the borehole. So we've got 10 out of 18 that we've got to eliminate. And that was pretty good. We had late left, and then we went to Trenton. And we had 6 of them hit groundwater in an hour. 3 more over 70%. But we still had a couple of them that were hanging in there. So we're down to maybe 4 or 5 recipes that we felt really good about in the Vado zone. Remember the environmental folks? Okay, here they are. Here's their results. Guess which 2 were the 2 they thought would be the answer? That's the bentonite polymers and the bentonite catalysts. And we got 58% and 67% of the grout column compromised in an hour. They were high water content slurries once again. If you look on the left-hand side of the chart, their 9-to-1 sand to bentonite ratio, 24%. And this is an average of all 3 sites. So that's acceptable, but hey, clear over to the left. Their dry mix, 3%. They matched a dry borehole with a dry mix, and only 3% of the grout column was compromised. We have found that high solids content in an environmental well, which is mostly all Vado zone, is the only way to protect that groundwater. A high water slurry is not going to be effective. The direct push, folks, it really didn't matter much if you treated the bentonite with soda ash or you didn't. That really is statistically insignificant when you look at over 80% of the grout column compromised in an hour. And the problem with the direct push is they just can't get a big enough angular space to get enough solids in there to protect the borehole. To show you that, this is a video of a monitoring well installed by direct push methods. We're going down a 2-inch monitoring well. You already see the dyes penetrated in front of us. We're coming to static water table, and this is the only time in the study we saw a bentonite crack below static water table. In fact, not only crack below static water table, it allowed dye to penetrate below static water table. Now, to be fair, this is in a kind of a semi-confined aquifer where once you penetrate the production zone, the water table is going to rise up into the clays and the soils. But when we compared this with all the other wells on site that had a large enough annular space, we never saw the cracking and we never saw dye penetration. So the logical conclusion is there's just not enough solids in this borehole in order for this to provide protection. Now, I want to say a word just a minute here about direct push. Direct push is a fantastic technology for what it's designed for. Direct push will come in and give you a biopsy of an aquifer. It'll delineate a plume quickly and cheaply. It's designed for investigations, okay? Trying to make a permanent situation out of an investigative tool is not going to be effective here in Nebraska. And I'm sure the folks behind this technology are going to adapt. By participating in the study, they found out where they need to get better, and I'm sure they will do that. But for now, direct push is used as a temporary well in Nebraska. Rotary mixes. Okay, this is all the rest of them. This is really interesting. Let's go over here to the chart again. If you stand back and look at the chart, you're going to see dramatic differences right here. Okay? Anything this side of the chart, when you look at it, is a high water content. It's a high water slurry. And look at the results. Over 50% is compromised. And hey, look at here. Drill cuttings. How can that be? This is the same material that came out of the borehole. How come we got 57% compromise off the same material? Well, after looking at this, we came to the conclusion that while it's the same material, we cannot replicate the compaction that this material is placed in. In other words, when you drill it up, you destroy the compaction. When you destroy the compaction, you destroy the sealing capabilities. That's why we don't allow drill cuttings as a grout in the state of Nebraska. But let's go over to this chart. This is how we construct domestic wells in the state of Nebraska. I felt really great about that. Only 10% of that column was compromised. So we know our drinking water wells were pretty well protected. Here's the cement with a fly ash additive, 9%. These two are almost identical. Here's our gravel, 3 parts gravel with 1 part chip. Here's our sand with bentonite, volume to volume ratio. Here's a sand with a cement bentonite. This is a high solids, 1 part sand to chip. Here's the IDP with cement. So high solids contents, we got less than 30% penetration of the vadose zone. That was a lot of fun. So this is the best video of the whole bunch. This is a nice, tight, neat cement. Look at that. It's got a little horizontal crack. Not bad though. There's not a wrinkle. There's not a crease. There's not a flaw in this thing, man, and water's passing it between it and the casing. Look at that. You bond log this thing. You use the old technology and bond log this. They would tell you that's perfect grout. If you didn't have a visual component, you wouldn't know about a microannulus, and this is where we learned where cements don't bond to PVC. During the heat of hydration, the cement gets hot and it softens the plastic. Okay? When the cement cures and dries, it recedes and draws back, and the plastic goes back to its nominal size. And it creates a microannulus not much thicker than a sheet of paper. But without that bonding, we don't have a seal between our grout and our casing. But we've got great structural stability. So, cement really does not bond to all materials like we were told. It really is not the universal grout material like we thought it was. It has some fantastic universal properties. But now we know that there's truths and there's myths about both cements and bentonites. But I want to give you some really, really exciting good news, okay? For our geosystems, our geoloops, the dirty sand experiment worked really, really well. The dye test showed that we only had dye movement of about 5 feet in an hour and no change in 24 hours in that dirty sand. When we went back 30 days later, we didn't see any change. We went back 90 days later, no change. And it provides superior thermal transfer because we have full contact with the loops. We have now solved a problem for our environmental folks, and we have now solved a problem for our geothermal folks. The only thing left to decide here is how to come up with an effective way to place this sand so it's easily placed, so it meets our 4th parameter. And I think we've done that. So this gets us into the unconventional thinking new results portion of the program. Dave Hansen is a past McEllhiney lecturer. He's the owner of Design Water Technologies. And he told me as part of our task force when we first started this, Tom, I don't think you can seal the borehole in Nebraska. I said, Dave, you're crazy. Of course we can seal the borehole in Nebraska. Do it all the time. Man, we would be in big trouble if we couldn't seal the borehole in Nebraska. Well, I studied all the videos. I looked at every one of them. Over 8 to 9 years, 128 wells, foot by foot, and it really pained me to say this for the first time because he was sitting in the audience, but he's right. We cannot seal the borehole in Nebraska. You know why we can't seal it? Because the ground we're drilling in isn't sealable. If it was, we wouldn't have groundwater. Okay? If we could seal it, we wouldn't be a groundwater generator. Our state was designed to collect and store groundwater. That's what it does. That's what the unsaturated zone does. And if you put a high water slurry in that filtration system, it's going to take the water out of it and store it. That's what the design is. So rather than fighting against Mother Nature, insisting that Mother Nature do something she's not wanting to do, if we want to protect groundwater in Nebraska, the best thing we can do is protect the filtration system. And when we drill a borehole through it, we can't allow grouts that crack and channel and bypass the filtration. We have to have grouts that divert everything back to that filtration system and let the world do what the world was designed to do. Okay? Reconstructed conditions in the borehole that mirror the surrounding soils in the unsaturated zone, then we can provide groundwater protection. So what's needed? Well, I'm going to tell you a little story again. Told you I was a contractor for 20 years, right? Well, as a contractor, I didn't much care what was between the production zone and the surface, because I got paid when I got to the production zone. That's where the water was at, that's where the money was at. So my well logs didn't pay much detail to the surface geology. That's exactly the wrong thing to do after looking at the results of this study. We have to pay more attention to that geology in the unsaturated zone. We have to write down everything on the well log where it occurs. We have to have the accurate descriptive language telling engineers and designers of wells what we've penetrated, and we've really got to be more meticulous every time the bit starts in the ground. What's the best method for grouting? What's the best material? There really, folks, there's no magic bullet. There's no cookie cutter. There's no material you can say, use this every time, you'll have universal protection. There isn't such a thing. You have to match the grout composition to the on-site conditions, much like we discovered when we put a sand cement in a sand aquifer. Okay? And this will work either if you're in consolidated soils or unconsolidated soils. All right? And there are no shortcuts. If there's any folks out there watching that drill test holes for a living, let me tell you this. You should be the highest paid person in your company. Because if you're a test hole driller and you do the test hole like it should be done and you get the right information and you get it right, everything else is easy. Really is. If you don't get it right, no amount of talent, no amount of engineering, no amount of makeup is going to make up for that lack of information. And in the end, the best application may be a composite. You may have a bentonite, you may have a dirty sand, you may have a cement all together in the borehole. So, in summary, the new truths, and remember this, please remember this. All grout materials are going to perform within their given properties, and they do not change. We tried for 8 years to make a high water slurry work in situations it cannot work. We tried for 8 years to make cement not crack. Okay, I've learned there's 2 types of cement in this world. There's cement that's cracked, and there's cement that's going to crack. So remember, bentonite slurries, if they can stay wet, if they retain their water, they're going to perform. Inert solids like sands and gravels will improve that performance, but folks, if they crack, they will not rehydrate once they're damaged. Bentonite chips will rehydrate, but they can really be tough to place in the borehole, and it could be a long time to make sure they get down to the place where they got to be. But if you get them placed, they will give you the most dynamic performance of any reactive solids we found. And cements will crack, but cements will give you great structural stability. They will ensure the top integrity of your well, and they have a place in the grout column. But just remember, cements will not bond to PVC, so you're going to have some sort of a bentonite or some sort of other dynamic seal below that. And neat cement has the properties to intrude through chips. So lower the water content the lowest you can. A sand blotter is needed when used with chips. So where does Nebraska go from here other than the Big Ten? That got a lot of laughs in Big 12 country, let me tell you. RPWS people, based on the findings of this study, now require bentonite chips from just above the screen openings throughout the whole borehole, and the wells must have a surface protection of cement or, if applicable, chips, depending on the conditions. All right? Full-length protection of a dynamic seal we feel is going to protect our towns, our cities, and our communities, give them the best possible protection. For our private systems, we are in revisions of our well standards, and we're going now with some different ideas. We're all focusing on water quality instead of water quantity. We always have had a surface seal, but now we have an aquifer seal. We're going to put a seal down on top of the aquifer as a primary seal. The surface seal is going to be a secondary seal, and we're going to have high solids fill material in between. We're not going to allow anything for closed loop or geo systems that don't have a high solid sand content in them. No longer just a bentonite slurry, because we know they don't work. We're going to look at minimal screening and full-length grouting in areas of high water quality concerns. And there's one more neat little story I want to tell you about Clarks, Nebraska, that we learned. Clarks is a town in central Nebraska, gets its water out of a homogeneous aquifer. It's all sands and gravels, maximum 114 feet deep. Clarks struggled with uranium in their water. So in order to address that, Clarks went outside of town, found a site that had 0 uranium, drilled a test well, and developed it, and wow, let's do this. When they put out their production lines and developed the wells and put in the new city wells, first month they had pretty good results, but slowly but surely their well started climbing up into that 120 picocuries per liter for uranium. Well, how does this happen? How does an aquifer go from 0 uranium to 124? Well, we called back the folks from Direct Push, Geoprobe, and they have a neat little tool that inserts water through the point as they're mapping the aquifer. And they were able to delineate 3 to 4 aquatards within that aquifer that were no thicker than that cell phone. Okay? I told you I was a water well driller, and I was a pretty good driller when I come to the production zone, but there's no way I would have found an aquatard this thick. So when they found those aquatards, they constructed integrated wells in a step pattern so they could measure the uranium content. And what they found at the bottom? 0 uranium. The next level up was about 30 picocuries per liter. The next level up was about 60. The top level was 120. Then we got to looking at the construction of the town well. The town well had 80 feet of screen in it, big borehole, and gravel packed the whole annulus. And what we did, we commingled the waters. All right. That was another lesson learned. Homogeneous aquifers don't have the same water quality throughout. We know there's different water qualities in a sand gravel bed aquifer. So our standards are looking now at addressing that concern. If we know there's a contaminant, we're recommending minimal screening and full length grouting in those areas. We're going to have a steel segment through the frost zone with a cement seal because we're confident the cement will bond to steel. We're no longer allowing any grout slurries without high solids for any reason above the unsaturated zone. And for the first time, we're going to have a uniform grout standard, whether it's for potable wells, whether it's for livestock wells, or whether it's for irrigation wells. We're all drinking out of the same pitcher of our wonderful aquifer, so we're going to protect it in a uniform standard. There are future studies that are coming on the horizon. Now, Nebraska knows what Nebraska needs to do to protect our groundwater. We moved ahead with those standards, and we feel real comfortable about that. But because we have the study laboratory for the nation, our bentonite folks have asked us to consider studying calcium bentonites, pelletized bentonites, cement and steel pipe, and then we're going to look at a process called microcells that I learned about in Australia that they use for their cement solids. But what microcells do is they lighten the weight of the column and they maintain the high solids content. So there are more studies coming. The grout study is published. The University of Nebraska has that for sale at their MAPS room. It's about a $30 charge. The Vadozone study is not published yet. It will be here in the future. And any other future studies will also be published through the university. Now, I want to tell you something personally. This has been a wonderful, wonderful year for me. It's gone by really quick. And I've gotten so much out of this opportunity to be a McEllhiney lecturer. And I learned early, if you want to make a difference, you get involved, okay? I'm the type of person that if I go to a meeting when I was a contractor and I didn't like what was being said, I had the right to remain silent. I just didn't have the ability to do it. So I raised my hand, and that got me on a committee. And that committee got me involved with my local health department. That local health department led to being involvement with the state. And the state led me to be involved with the national. And this is how a well driller from eastern Nebraska goes from drilling private wells to talking all around the world about dirt, rocks, and water. You get involved. Because decisions are made by those who show up. It happens every time. If the people that have the experience, the boots on the ground experience, don't show up to these meetings, the planners don't have the benefit of your knowledge. And if we're going to have a new focus on water quality, we've got to start with a good design, focused on that. And we've got to couple that with good construction and a commitment from our industry, commitment to excellence. And if we can do that, we're all going to have a brighter future for the groundwater industry in Nebraska and hopefully other states and the countries around the world that have talked. But it all starts with you getting involved and becoming interested in how you can improve the process. Now, there's a lot of credit that goes on with this. And I want to thank personally our partners of Baroid, Wildman, and Setco for providing the expertise and the products to make this study happen. Without their cooperation, there's no way we can pull this off with all the different dynamics we come up with. I want to thank my state. My state I'm very proud of. When we discovered that bentonites didn't do what we thought they did, my state had the courage to stand up, fund it, back it. Our administration fully went behind it, and I'm very proud of that. And because of that, we came up with new solutions that will hopefully help not just Nebraskans, but everyone else that is interested in protecting groundwater. I want to thank the university, the departments of DEQ and HHS for combining the task force and the manpower and dedicating the resources to this. This is a major, major drain on resources, but it has a major, major impact. And I want to thank the NGWA for giving me the opportunity to share this with you out there and folks around the world. And finally, if you don't remember anything else about this lecture, remember this slide. Because this is why we do what we do. This is why I do what I do. And if you can't read the quote, that's from Wally Schirra, a NASA astronaut, that says, 3 times I left the planet and found nowhere else to go. So please take care of the spaceship we call planet Earth. And that sums it up about as good as I can. So with that, ladies and gentlemen, that's the conclusion of the 2011 McEllhiney lecture. And we have people standing by if you want to phone in some questions. We'd be more than happy to answer them. Well, I guess we have no questions, so thank you for attending, and I hope you enjoyed the presentation.